The James Webb Space Telescope has already marked the start of a new era in the study of extragalactic astronomy, even after only a few brief weeks of operation. A few candidate galaxies have already been found by the infrared observatory that counters both the Big Bang theory and our understanding of the galactic evolution model. So, in this video, we're going to walk you through the James Webb Telescope discovery of the farthest star ever, which is mind-blowing. Now let's get started. In an effort to learn more about this specific object, the Webb Observatory has currently pointed all of its instruments in the direction of Irondale, the most isolated and distant star known to exist in the known universe. Light travels to Irondale in many years, which is unfathomably lengthy. This indicates that the star existed before the universe had been around for a very long time. Old Irondale may be a member of a unique group of stars that astronomers have been looking for more than half a century, but the question is, how can researchers find a single star? What makes Irondale unique in comparison to the other stars that we can see around us, even so far away in the universe? And more crucially, how do the most recent observations of Irondale by the James Webb Space Telescope contradict our beliefs about stellar evolution? Now, let's get to the answer to these questions. The time it takes for light to get to Irondale is quite long, but the actual distance between the two places, taking into account the expansion of the universe, also takes some time. As a result, we are truly viewing the star in the form that is assumed many light years ago. Because of this, the Sun and the Earth are both significantly younger than Irondale. Irondale is the first isolated star to be found at such a huge distance. Up until this point, the smallest objects that had been observed at these distances were star clusters that were included in extremely far-off galaxies. This star was identified with the assistance of the Hubble Space Telescope. The first thing that Hubble saw was the star's parent galaxy, which was seen through a gravitational lens created by a cluster that was in the foreground of the image. When a galaxy cluster or other extremely massive astronomical object is located in close proximity to one another, the fabric of space and time around these objects become twisted, which causes the light from nearby foreground celestial bodies to bend. Under specific circumstances where there is an exact alignment, the light coming from individual stars can be magnified by the foreground clusters thousands of times. The researchers did, however, identify a bright object that was resting on the border of the distorted galaxy. Sources in faraway galaxies are normally quite intense. The astronomers referred to the background galaxy that contained Irondale as the morning arc. This was because the background galaxy appeared to be an arc. Novas, supernovae, and tidal disruptions caused by black holes were observed. These are called transients, and it just so happens that their brightness shifts over time. The observations made by Hubble, on the other hand, revealed that the brightness of this object had not changed for more than 3.5 years. Due to the fact that its wavelength is limited, astronomers came to the conclusion that it is a gravitationally lensed bright star in the sunrise arc. Since Hubble could only provide a limited amount of information about this faraway star, astronomers decided to use the James Webb Space Telescope to examine Irondale's features. In addition, the research for this study was directed by Dr. Brian Welsh of Johns Hopkins University. In March of 2022, he and his team made the discovery of the star. They used data from the Hubble Space Telescope in their study, and they evaluated new photographs of Irondale obtained by the NIRCam instrument on the James Webb Space Telescope. These pictures cover a spectrum of wavelengths ranging from 0.8 to 5 microns. Irondale was analyzed in 8 different Webb filters, and the exposure period for each filter was greater than half an hour. There are 3 important takeaways to be taken from the most recent observations made by the James Webb Space Telescope. The first thing to consider is the star's redshift. The redshift of deep space objects provides a measurement of how far apart they are. The redshift is represented by the dimensionless quantity z, with z equal to 0, marking the present time. As the value of z increases, the look-back time also increases, as does the distance to the object in question. Irondale has been found to have a redshift of 6 according to recent online observations. This value makes Irondale the highest redshift star ever, and it is consistent with the Hubble Space Telescope data that were released in early 2022. The star's bolometric brightness, or the amount of energy it emits over the whole electromagnetic spectrum, is the next significant aspect of Irondale to be noted. According to the Webb data, Irondale cannot be a low-mass star, brown dwarf, or free-floating exoplanet that experience gravitational lensing. Instead, the data reveals that it is a B-type star with an effective surface temperature of 13,000 to 16,000 degrees. According to their surface temperatures, stars in the universe are primarily classified into 7 categories: O, B, A, F, G, and M. The difficulty occurs when we attempt to calculate Irondale's total illumination, which is between 600,000 and 1 million times the brightness of the Sun. This means that if Irondale is just a single evolved star, its mass must be 40 times that of the Sun. Alternatively, this light could come from 2 stars with 30 solar masses or 5 stars with 20 solar masses. If one assumes that the surface temperature is about 15,000 Kelvin, the researchers note in their paper that a single star is not the only explanation for the spectral energy distribution plots. Because of this, the possibility that Irondale is a system with more than one star cannot be ruled out. Massive stars that we observe around in our local universe commonly have companions, and in many cases, they have multiple companions. The tertiary companions might be up to 20 astronomical units away from the star, but the primary companions are within 2 astronomical units of it. Therefore, if Irondale has companion stars, the resolution power of the James Webb Telescope prevents it from seeing them. Another issue is that the star will exceed the Humphreys-Davidson limit, or the HD limit, if it is 1 million times more brilliant than the Sun. The HD limit is the empirical luminosity limit, above which, at least in the local universe, no stars have been seen. Therefore, we may need to re-evaluate the HD limit and set new limitations on it if Irondale is discovered to be a single star with 1 million times the luminosity of the Sun. The significance of Irondale's discovery is important because it lies in the possibility that it marks the first observation of a population of 3 stars, for which astronomers have been searching for many years. Helium and hydrogen are the 2 principal chemical elements created by primordial nuclear synthesis. In astronomy, the earliest generation of stars, referred to as population 3 stars, had traces of metals. Metal refers to any element that is not hydrogen or helium. Astronomers assume that the majority of the population of the 3 stars has died, and the surviving ones are difficult to view due to their dimness. They are nearly impossible to spot. Naturally, given the majority of candidates have been found in gravitational lens galaxies, astronomers anticipate that Irondale will continue to be significantly magnified for many years. The next observation of Irondale with the James Webb Space Telescope is arranged for December 2022. Accurate measurements of Irondale's luminosity and surface temperature would help determine its type and stellar life cycle stage. Additionally, astronomers anticipate discovering that the Sunrise Arc galaxy is devoid of the heavy metals that form in subsequent generations of stars. It strongly suggests that Irondale is an extremely uncommon, huge metal-poor star. The search for the first stars in galaxies has been astronomy's holy grail. The discovery of the first generation of stars would aid our understanding of star creation and validate the Big Bang's model's prediction. Additionally, looking for them is analogous to looking for our own roots. According to Richard Feynman, the most amazing finding in all of astronomy is that stars are composed of identical atoms to those on Earth.